Okay, so this is the first result that we had. Now let's just talk about what does it mean. So you've got the commutator between m mu nu and p alpha. Now, if you calculate the commutator between m mu nu and any operator O, what this is going to tell you, you'll get a delta O. And what this is telling you, um, it tells you how, how O transforms under a Lorentz transformation. Okay, so that's what this commutator is telling us. Now, why is this an interesting thing to pay attention to? Well, for the following reason. So P alpha is a D vector. It's transforms as a vector in D-dimensional space-time. So if, for example, we were in four-dimensional space-time, then P alpha would be a four vector. But if we take a look at I, m mu nu, and now let's just make that a bit nicer, m mu nu, and now we act on k alpha. Well, we know that k alpha is also a D vector. In 3 plus 1 dimensions, k alpha would also be a 4 vector because it carries a single vector index. So all 4 vectors transform in the same way. All D vectors in D dimensions transform in exactly the same way. So on the right-hand side, we'll have the following. Eta alpha nu k nu minus eta alpha nu k nu. So what you can see is everywhere that there was a p in my boxed equation, I've now replaced by a k. I got this equation by thinking about Lorentz transformation properties of k alpha and p alpha. They must transform in the same way under the Lorentz group because they are both vectors. Okay, but now you can calculate this special conformal generator commutator with the Lorentz generator exactly as we did for the Lorentz generator in momentum, and you can verify the boxed equation that I've just written down. Next, so we can still use this logic further. If we think about a scalar, well, you know that for a scalar, delta O would be equal to 0. And in particular, one scalar that we know of is the dilatation generator. That doesn't carry any indices. It's a scalar. So we immediately get that I, m mu nu, commutator with D, well, D doesn't transform, it's a scalar, is equal to 0. So check that. See if this really is equal to 0 or not. You can verify it. And then finally, we've got one more commutator that we want to consider. We could consider I onto m mu nu. So the Lorentz generator again, but now we'll let it act on m alpha beta. And one of the things that I'm sure that you saw in your course on special relativity is that each index on a tensor transforms in exactly the same way. So if we look at how m alpha beta transforms under a Lorentz transformation, we can first leave the index beta alone and transform the alpha index, and then we can leave the alpha index alone and transform the beta index. So first let's transform alpha. And using the rules that we've been using above, this is eta alpha mu. Then we'll have an m nu, and we leave beta alone. Minus, we'll have an eta alpha nu, and m mu, and we leave beta alone. And now, so this is when we transform the alpha index, we leave the beta index alone. Now, let's leave the alpha index alone and transform the beta index. So we'll get eta, beta, mu, m, alpha doesn't change, nu, minus n, beta nu, m, alpha doesn't change, and we've got mu. So there we go. So we've managed to write down another 3 commutators, which you should check, but using only Lorentz invariance. So that's great. Now let's move on to commutators between the dilatation generator and the momentum. And the first commutator, so just calculate this by hand, is ID, comma, P mu is equal to P mu. Now remember that P mu is length to the -1. So it scales in a definite way. And that's why it looks like when d acts on P mu, it gives us back P mu. P mu is an eigenfunction of d. If we look at K mu, well, K mu is a length. So we can immediately write down the following commutator. So you should check both of these. But we can really write down, it looks exactly the same, but there's a minus K mu. Why? It scales in exactly the opposite way because it is a length, not an inverse length. And then finally, we know that M mu nu is dimensionless. And that means that I d comma M mu nu is equal to 0 because it has no dimensions. So this final commutator, we argued based on scaling. So these 3 we argued based on scaling. So these 3 we argued based on scaling. These commutators over here, we argued based on Lorentz. So this was on Lorentz. But notice that the argument based on Lorentz has given us exactly the same as the argument based on scaling. So that's nice. We've got 2 independent ways of learning that d commutes with M mu nu. And then there's one final commutator that you should calculate. Again, check this. And it tells us that I P mu, comma, K mu is equal to. Now remember that P is an inverse length, K is a length. So an inverse length times a length is dimensionless. So whatever we write down now on the right-hand side has to be dimensionless. And if you go ahead and calculate this carefully, you'll get -2 M mu nu. Well, we know that M mu nu is dimensionless. And you'll get +2 eta mu nu and the dilatation operator. And that's the last commutator in the Lie algebra. At this point, we've gotten all of them. So this one we calculated, okay? So this commutator over here, we did by hand. So we can say by hand. These next 3 we predicted just by using Lorentz invariance. And then these 3 commutators of d with p mu, the first one again, you would need to do by hand. But once you've done it by hand, knowing that the dilatation operator's actions are related to the dimension of the things that it acts on, you could easily get the next 2 commutators, d comma k mu and d comma m mu nu, by using a scaling argument. And then finally, again, this last one, you would need to do by hand. But these arguments based on scaling and based on Lorentz invariance are particularly useful because they give you a nice conceptual understanding of why the commutators look the way they do.